Today we're going to talk about explicitly trying to find good policies for your problem. Sometimes explicitly learning the Q function or the value function doesn't work very well because, for example, your state space may be too large or you cannot find relationships between similar states. And if you use a feature-based representation, like we'll talk about today, you can sometimes do better to generalize more quickly. But the drawback is that when you use these feature-based problems, you can't necessarily estimate the Q values very well. And so what we'll do instead is try to explicitly find policies that maximize our rewards. Here's an example of a robot trying to fold a towel. This is actually a very difficult problem for a robot to do because towels are deformable and soft, and so you have to use techniques like this to learn what a robot should be doing at a particular state. One successful example of explicitly learning policies is called imitation learning or apprenticeship learning. And so here you have examples from some expert. And these examples are a clue about what your agent should do. And so now you can basically learn this as a classification problem that given a state that looks like this, you should do action A. So this seems very straightforward and reasonable, but think about what reinforcement learning actually is. And so the problem is that if you go off a state trajectory that you haven't seen before, this could lead to problems. So what we need to do is provide ways for our agent to compensate when it gets into states that the expert examples haven't been in. So we find good examples of policies either from experts, or sometimes we can solve this explicitly with dynamic programming, and then we're going to represent each state with a feature vector. Then we train a classifier on that data, and that classifier now becomes a policy, and we can execute that policy through our state space. But this learned policy is not going to be as good as the expert policy that we're trying to emulate. And so what we can do is we can interpolate between these two policies. One important detail is that as we train this policy, the loss is going to be related to the reward that you get from following this policy. And so there are a number of ways to do this. We're going to be talking about SEARN from Haldane, but there are other related algorithms that do similar things, such as Dagger. So these systems have been used for a number of different applications, including flying helicopters, driving cars. Some things that I personally have worked on is doing question answering and machine translation. And since I know these examples a little bit better, I'm going to talk about these. One example is playing trivia games where you get the question one word at a time, and after every word you need to decide, do I have enough information to answer this question or not? And when you're competing with many different people, this becomes a reinforcement learning problem because you need to understand what kinds of actions your opponents are likely going to take, what the agent itself knows about this question, and use that to figure out what should be your optimal strategy for answering these questions and when to answer those questions. And so here the action space is very simple. You either wait for more information or you answer the question. This is called buzzing in the terminology. And because it's a game, there's a very nice formulation as a reinforcement learning problem where the points that you get become your reward. Machine translation is also a similar reinforcement learning task. And so here you have words coming in one at a time. And we don't just want to translate entire sentences. We want to translate as aggressively as possible. And so this is what actually happens when you're at the United Nations or things like that. You have words coming in, and you have these very skilled, highly trained interpreters who are listening on headphones and are translating immediately. And so this becomes difficult, particularly when you have languages that have different word orders. And so in languages like German and Japanese, the verb often comes at the end of the sentence. And so if you're trying to translate that into English, where the verb is somewhere in the middle of the sentence, you have a long time to wait if you want to translate the verb into English. And so you can do things like reorder the sentence, or you can try to predict what the verb is going to be. So we're going to use this as our action space, that you can either predict what the verb is going to be when you're getting a German or Japanese sentence coming at you, or you can translate what you have thus far. So these become our actions that you take after hearing every word of the German or Japanese sentence, and your reward is the quality of the translation that comes out. So just to make this a little bit more concrete, if you had a psychic policy, so this is obviously not workable, you would hear one word in German, er, for instance, and then you would translate that as he went to the store. And that's a perfect translation, and so you get a great reward. And so you've done it super early, you've done it completely accurately, you get maximal reward. If you just translated the sentence one word at a time, every time you see a word, you get some reward. And so you can say, he to the store went. And this is an okay translation, and you're doing it very promptly and very quickly, so you get some reward all along. The overall structure of the sentence doesn't quite match what an English sentence should look like, so the overall score is a little bit lower. If you wait until the very end of the sentence, you can do a better job because you have the verb. And so you wait, and you give up a lot of reward by waiting so long, but once you see what the verb is, you can translate the sentence in its entirety, and you get maximal reward at the final time step, but you've lost out on reward all along, and so you're not able to accumulate additional reward. What we would like our system to be able to do is to have a richer action space where instead of just translating the words that it's seen, you could also do things like predict words that you haven't seen yet. And so if you can have the best of both worlds between, say, the monotone and the batch translations, by predicting what the verb is going to be, you can start collecting reward early by translating words that don't depend on the verb as soon as you see them. And then once you have enough information where you could maybe guess what the verb is going to be, you could predict what the verb is going to be, get additional reward, and then translate the rest of the sentence as it comes in. And so you have the best of both worlds. You're aggressive enough to translate early parts by predicting what the verb is going to be, and you haven't made any mistakes. So this is the kind of thing that we want our algorithm to do. How do we use imitation learning to do this? So we have some examples of a good policy that we want to follow. We can either figure this out through an algorithm, or we can get examples from expert translators. And so we get a bunch of examples of states and the actions that we should take in those states. And then we learn a classifier. And so we represent each state as a vector of features, and we have what we want to do in that state. And so our actions become labels, and we try to predict those actions given a state vector. And the loss is based on the reward that those actions receive. And as you know from working on machine learning, classifiers are never perfect. And so it's not going to follow the same state trajectory that the original classifier did. And it may be a pretty lousy student of the expert. How do we solve this problem? As we follow the interpolated policy, when we reach a state, we're going to flip a coin and decide which of the two policies we're going to follow. We're going to combine our good policy with bad policy. And so we now have a combination of these two policies, and this provides us with a new training set for a classifier. So we're going to take those state action pairs interpolated from our two policies, train a new classifier based on those, and then hopefully that classifier will be able to follow this new state action sequence. And to think about this intuitively, imagine that you're learning to drive from a Formula One race car driver. And so this driver is going to do tricks that a person who can't put their car into reverse could never ever do. So what you're going to do is you're going to force the expert policy to be in situations like being stuck in the ditch alongside a road that the stupid learner policy gets into, and see how they react to those situations, and use that to cover the state space more broadly so that you're able to adapt to cases when the student has made mistakes. So what we've seen today is how we can use features to parameterize our state space. And this is useful when you want to do things like imitation learning. However, you still have to specify the features. And one common theme that we've seen in this course is that we don't want to be defining these features. Can we use deep learning to do something similar? And that's what we're going to talk about next. How can we use deep learning to learn policies explicitly and to learn features that do the best job of generating good policies?